Good morning. Today we're going to talk about section 6.1, velocity and net change, and this is the last section for the Calculus 1 series here at UIO. So in previous chapters, we established the relationship between position and velocity of an object moving along a line. That is, velocity is the derivative of position. With integration, we can now say much more about this relationship. Once we relate velocity and position through integration, we can make an analogous observations about a variety of other practical problems, which include fluid flow, population growth, manufacturing costs, and production and consumption of natural resources. The ideas in this section come directly from the fundamental theorem of calculus, and they're among the most powerful applications in calculus. So here's just some quick bullet points as far as definitions go for position, velocity, displacement, and distance traveled. The position of an object moving along a line at time t, denoted s of t, is the location of the object relative to the origin. The velocity of an object at time t is v of t equals s prime of t. That is, velocity is the derivative of position. The displacement of the object between t equals a and t equals b, where b is greater than a, is s of b minus s of a equals the integral from a to b of v of t dt. While the distance traveled by the object between t equals a and t equals b, where b is greater than a, is the integral from a to b of the absolute value of v of t dt, where the absolute value of v of t dt is the speed of the object at time t. So displacement and distance traveled are two different concepts. It's like talking about how much area is there in total between a curve and an x-axis and the net area. So one has positive and negative contributions. Displacement will have positive and negative contributions, while distance traveled will only have positive contributions. So let's do some examples. In this first example, we've got a jogger that runs along a straight road with velocity measured in miles per hour, given as 2t squared minus 8t plus 6 for the interval 0 to 3, where t is measured in hours. The first thing we're going to do is graph the velocity function over the interval 0 to 3, then determine when the jogger moves in the positive direction and when she's moving in the negative direction. Find the displacement of the jogger in miles on the time intervals 0 to 1, 1 to 3, and 0 to 3, and interpret these results. And then finally, we're going to find the distance traveled over the intervals 0 to 3. So the very first thing we're going to do is graph the velocity function over the interval 0 to 3. And I've just used a graphing utility, Wolfram Alpha, to graph this. And we can see that we have intercepts at 1 and 3. And I'm even going to do, so our velocity function is 2t squared minus 8t plus 6, which is also equal to 2 times t minus 1 times t minus 3. So we see from our equation and both from the graph that we've got an intercept at t equals 1 and t equals 3. Now, the velocity is positive, that is, it's greater than 0, between 0 and 1, and it's negative between 1 and 3. And this just means that we're moving away from the origin from time equals 0 to 1, so we spend the first hour moving away from the origin, and then our velocity crosses the x-axis, or the t-axis, I should say, which means we stop moving, and then we turn around and we've got negative velocity, which means we're moving in the negative direction. So for the next 2 hours, we're going to move back towards the origin. The next thing we want to do is find the displacement of the jogger in miles on the time interval 0 to 1, 1 to 3, and 0 to 3, and interpret these results. So the displacement in miles from over the interval 0 to 1 is s of 1 minus s of 0, and it's going to be the integral from 0 to 1 of v of t dt. So I'm just rewriting using our equation for velocity And then I'm going to go ahead and integrate, and I get 2/3 t cubed minus 4t squared plus 6t evaluated from 0 to 1. When I plug in 0, all of my numbers are going to go to 0. When I plug in 1, I'm just going to get the coefficients. So I get 2/3 minus 4 plus 6. And all of that comes out to equal 8/3. So from 0 to 1, we travel 8/3 of 1 mile. So 2 miles and a little bit more than that. Now we're going to do the calculation. For the interval 1 to 3. We get the same thing, but we're just evaluating at different endpoints. So 2/3 t cubed minus 4t squared plus 6t evaluated from 1 to 3. And when we do that, we get negative 8/3. So we travel negative 8/3 of 1 mile. And the negative means not that we're traveling a negative distance, just that we're traveling backwards towards the origin, right? So we spend the first hour, we travel 2 2/3 miles away from the origin, then we stop, spend the next 2 hours traveling in those 2 2/3 miles back towards the origin. So over the interval 0 to 3, the displacement is going to be 8/3 plus negative 8/3 or 0, which means just that after 3 hours, the jogger returns to their starting point. Now we're interested in finding the total distance traveled over the interval 0 to 3. So we want only the positive area under the curve. So we're taking that absolute value. So we know that we're looking for something This is the graph of the absolute value of our function. So we get this negative portion, what was negative 8/3, gets flipped over our t-axis and becomes positive 8/3. So the total distance traveled is 8/3 plus 8/3, or 16/3. And if you really want to be precise about it, you can integrate the speed and get the same result. But there's not really a need to do that because we already know the two areas under the curve. So what about future values of the position function? Here's theorem 6.1. Given the velocity of an object moving along a line and given its initial position, s of 0, the position function of the object for future times, where t is greater than 0, is given as s of t, where t can be anything we like, equals s of 0 plus the integral from 0 to t of v of x dx. And here x is just a dummy variable, but the integral measures the displacement over the interval 0 to t. So let's work with some examples using this theorem 6.1. So we've got a block hanging at rest from a massless spring at the origin. So let me go ahead and draw this because this is maybe not so intuitive. Here's my block, and it's hanging from a massless spring, and it's just hanging there. It's at rest. So this is the position s equals 0. At time t equals 0, the block is pulled downward 1/4 of a meter. So the spring is elongated. and released. Its velocity in meters per second is given by v of t equals 1/4 sine of t for t values greater than 0. And we're assuming that the upwards direction is positive. So when I pull down on the spring, that's where I'm getting that negative sign for. And now we want to find the position of the block for t values greater than 0. So we're going to set up our function s of t equals s of 0 plus the integral from 0 to t of v of x dx, where x is a dummy variable. Now s of 0 we were given as negative 1/4, and our velocity function is 1/4 sine x dx. And we can go ahead and integrate. And when we integrate, the antiderivative of sine is negative cosine, so we pull a negative sign out, so we get negative 1/4 minus 1/4 cosine x evaluated from 0 to 1. Sorry, not 0 to 1, 0 to t. I'm going to copy all this work to the next slide. So when I go and plug in my negative 1/4 from s of 0 is still out there, minus 1/4 cosine of t minus 1/4 cosine of 0. Well, we know cosine of 0 is the same as 1. So this gives us negative 1/4 minus 1/4 cosine t plus 1/4. Our 1/4s cancel out. So s of t is negative 1/4 cosine t, which means our position function is given by negative 1/4 times this cosine function. So it's going to look something a little bit like this. It's going to look something a little bit like that. The next example that we're going to work with is about a skydiver. So suppose a skydiver leaps from a hovering helicopter and falls in a straight line. Assume he reaches a terminal velocity of 80 meters per second immediately at t equals 0 and falls for 19 seconds, at which time he opens his parachute. The velocity decreases linearly to 6 meters per second over a 2-second period, and then remains constant until he reaches the ground at t equals 40 seconds. The motion is described by the following function. Determine the height above the ground from which the skydiver jumped. So I'm going to copy this. And move it to, oh, nope. Oh no, what have I done? No. Okay. So this is our velocity function, and we want to know the height above the ground from which he jumped, which means we want to know the displacement. Sorry, we want to know the distance traveled by the skydiver. We want to know the distance traveled by the skydiver, which, because our velocity function is always positive, that is, the skydiver is always above the ground, the skydiver is never below the ground, the distance traveled is going to equal the displacement. So we can just use our displacement function. So we're going to say 0 to 40 v of t dt equals Now, we can't just integrate directly from 0 to 40 because we have these broken up intervals. So instead, we need to integrate as such. One integration from 0 to 19 of 80 dt plus an integral from 19 to 21 of 783 minus 37 t dt plus finally an integral from 21 to 40 of 6 dt. So what we get from that is 80t evaluated from 0 to 19 plus 783t minus 37 divided by 2 t squared evaluated from 19 to 21 plus 6t evaluated from 21 to 40. And when we do all that plug and chug math, we get 1720 meters. So the original height of the jump was 1,720 meters. That means the skydiver traveled that much distance during the course of the jump. Now, if we can do position from velocity, we ought to be able to get velocity from acceleration, and indeed we can. So given the acceleration of an object moving along a line and its initial velocity, v0, the velocity of an object for future times, that is t greater than 0, is given as such. v of t, where t is anything we like, equals v of 0, our initial velocity, plus the integral from 0 to t of a of x dx, where x is a dummy variable. So let's do a quick example. An artillery shell is fired directly upward with an initial velocity of 300 meters per second from a point 30 meters above the ground. Assume only the force of gravity acts on the shell and it produces an acceleration of 9.8 meters per second. Find the velocity of the shell while it's in the air. So we're looking for exactly that equation that we were just given. So v of t equals v of 0 plus the integral from 0 to t of a of x dx. And in this case, our initial velocity is 300 meters per second, while our acceleration is negative 9.8 meters per second. And why am I saying that? So our initial velocity is positive because it's pointing in the upward direction, whereas gravity is always pointing in the downward direction, so it's negative. So that's how I'm getting the positive and negative signs. So I'm left with 300 plus the integral from 0 to t of negative 9.8 dt. And all of that is going to, dx. And all of that is going to give me 300 minus 9.8 t. So that's the velocity of the shell while it's in the air. We can plug in any time t and figure out exactly how fast it's traveling. Now, we're not just limited to velocity, position, and acceleration. Everything we've said about velocity, position, and displacement carries over to more general situations. Suppose you're interested in some quantity q that changes over time. If you're given the rate q prime at which q changes, then integration allows you to calculate either the net change in the quantity q or the future value of q. Suppose a quantity q, this is theorem 6.3, suppose a quantity q changes over a time at a known rate q prime. Then the net change in q between t equals a and t equals b, where b is greater than a, is given as q of b minus q of a equals the integration from a to b of q prime of t, dt. Given the initial value, q0, the future value of q at a time t greater than 0 is given as q of t equals q of 0 plus the integration from 0 to t of q prime of x dx, where x is a dummy variable. And so let's do a quick example so that this makes some more sense. A culture of cells in a lab has a population of 100 cells when nutrients are added at time equals 0. Suppose the population, n of t, in cells per hour, increases at a rate given by n prime of t equals 90 e to the power of negative 0.1 t. Find n of t for t is greater than 0. So here we're just setting up n of t equals n of 0 plus the integral of 0 to t n prime of x dx. So our initial cell count was 100 plus the integral from 0 to t of 90 e to the negative 0.1 x dx, where x is just a dummy variable. So when we do that, we get 100 plus 90 divided by negative 0.1 e to the negative 0.1 x, evaluated from 0 to t. Working all of that out, skipping some steps because I can, because I'm the instructor, we get 1000 minus 900 e to the negative 0.1 t. And that's going to map out exactly how many cells we have at any given time. So that's it from me for nearly the whole semester. You're not going to get another video from me. But I hope you've enjoyed Calculus 1 as much as someone can enjoy a math class, and I hope that you feel prepared for the final exam. Feel free to shoot me an email if you need some more help or anything like that.